Welcome to the tutorial session for graph deep learning for time series processing, forecasting, reconstruction, and analysis. You are most welcome to engage with your organizers and each other in the Zoom chat function, Zoom Q&A, or on the tutorial discussions channel on Slack. Please note that the tutorial will be recorded and then uploaded to our YouTube channel for those who were unable to join or who would like to rewatch the session in the future. If you prefer not to be recorded, you are welcome to turn off your camera and participate in the chat. Now, without further ado, I will hand it over to our tutorial organizers.
Hi, hello everyone. Thank you for being here and for attending the tutorial. So I'm Andrea, and I will be the speaker for the first part of the tutorial. So these slides are available at the link that you can also find in the chat that we have just posted if you want to follow along. So let's start with a bit of introduction. So there are many applications where basically that are characterized by data that are continuously produced over time by multiple data sources, by multiple sensors. There are many examples of this. We have like traffic monitoring systems, sensor networks in smart cities, and also this is typical of many energy analytics applications, but also many applications in science, engineering in general, but also in financial market analysis, for instance. And all of these applications have one thing in common, that is that these time series, these temporal data, are characterized by rich dependency structure. So the standard deep learning approach over the years to process time series, in particular to forecast time series, has been that one of training a single neural network on large collection of these related time series. Within this framework, each time series is processed independently from the others, while the parameters of the model are shared. The main advantage of this approach is in its simple efficiency, since the model gets trained on data that come from many different sources. But the main downside is that in this way, the dependencies, this rich dependency structure that might exist among the time series is neglected. What we will see in the tutorial is how we can use graph deep learning to go beyond these limitations of the state of the art. So, as you know, since you are attending this conference, graph deep learning operators and graph representations allow us to embed these dependencies directly into the processing as inductive biases. And as we will see, the resulting models can operate on sets or subsets of correlated time series while still having the parameters of the model shared. Unfortunately, as we will also discuss, there are inherent challenges in applying this processing framework to data coming from the real world. So, as anticipated, the tutorial will present advances coming from the combination of deep learning approaches for time series processing and deep learning on graphs. And in particular, we will have a threefold objective, where the first objective is to provide a comprehensive framework to build these graph-based deep learning time series processing models. And at the same time, we want also to provide methods to address the challenges and the potential pitfalls in using these approaches in practice. And we will also be providing tools and guidelines to use these approaches to tackle real-world application and also for developing new methods of this kind. The presentation is complemented by a demo, so by a coding session that will happen at the middle of the tutorial, And the tutorial is also available in a paper format on arXiv, and you find the reference here. So it's also important to say what this tutorial is not about. So this tutorial is not about processing sequences of interactions, as typically done sometime when processing temporal networks. But as anticipated here, graphs will be a tool, a representational tool that we will use to represent the possibly dynamic relationships among a collection of time series. So this is an outline. So in the first part, we will be formalizing the problem setting we will be operating on. So that one of correlated time series processing. We will also present how graph-based representations can be used in this context. And then we will see how to build graph neural network architectures to process this kind of data. In particular, I will talk about an important distinction regarding these models, which is the one between global and local models. Then Ivan will be delivering a software demo, so the coding session, and both Ivan and Daniele will discuss the challenges in the second part of the tutorial. So let's start with the first part and with the problem setting. So for what concerns the kind of data that we want to process, we assume to have available a collection D of n correlated time series, and each one of the time series can be multivariate, so we can have multiple observations at each time step for each time series. Together with the target time series, we can have covariates. These are exogenous variables that might be somehow helpful in doing the processing. And these covariates can be both dynamic but also static. And in this case, we talk about attributes. We will use the capital letters to denote the stacked representations across the collection of time series, and refer to this dimension that spans the collection as the spatial dimension. So what are correlated time series? Why the correlated in the name? So we assume that data are generated by a time invariant stochastic process, and that there exists a causality a Lagrangian among the time series, which means basically that the forecast, the predictions for one specific time series can be made more accurate by taking into account observations at the related time series in the collection. Furthermore, we also assume that all of these time series are homogeneous, so that the observables for each time series are the same, have the same physical meaning, and that the observations happen synchronously over time and also regularly. We don't assume instead that these observations are generated by the same process for each time series. And so it's important to say that while this assumption might sound very restrictive in practice, they can usually be met with appropriate preprocessing steps and can also be relaxed, as we will see in the second part of the tutorial. Now, we can look at an example. Again, traffic monitoring systems are a classic example of this kind of scenario. And you can imagine to have many sensors spread around a traffic network, and each sensor will acquire some measurement regarding the traffic at its position. Can be like the average speed of vehicles, the number of vehicles, or things like that. And exogenous variables in this case can be like date time information, or also like weather prediction. For what concerns the static covariates, so the attributes, you can have information regarding like the type of lane the sensor is placed on, or the presence of traffic lights, or things like that. Clearly, in this kind of scenarios, there are strong dependencies among the resulting collection of time series. And this dependency will reflect the structure of the road network. So let's start to look at one of the main processing task that one is usually interested in performing when dealing with the time series, which is forecasting. And the objective here is pretty much straightforward. So the objective is that from a window of past observations, we want to forecast the next H time step ahead observations. In particular, we want to do that by learning a parametric model of the process generating the data. And in particular, in the tutorial, we will focus on point predictors, while probabilistic methods can also be considered. In particular, with point predictors, these are usually trained by minimizing a cost function that somehow measures the forecasting error, and using different cost functions, you can get predictions of different values. For instance, using the MSE, so the mean squared error, you are forecasting, you are predicting the mean of the stochastic process, while using, for example, the MAE, so the mean absolute error, you get predictions of the median of the process. Now, a first important distinction that we need to make when talking about forecasting architecture is that between local and global models. So local models are the family or models that have been typically used in the past for many decades to forecast time series by using like statistical methods like the Box-Jenkins approach. And the idea here is that you have a model whose parameters are specific to each single time series that you want to process, that you want to forecast. The advantage of this approach is that the resulting model can easily handle heterogeneity in the dynamics of the time series in the collection, since they are tailored to that specific sequence, to that specific process. The downside is inefficiency, which is an inefficiency which is both in terms of computation, since you would have to train many different models, but it's also an efficiency in terms of sample complexity, because again, you would need, you are using samples from a single time series to fit a model. At the opposite end of the spectrum, we have global models, which is what is typically done in deep learning. And here we have a single model that is trained on many time series coming from different sources. This is similar to what nowadays people call foundation models somehow, but usually here the scope can be more limited, like for instance to time series coming from a specific domain. The advantage here, again, is clearly, as anticipated before, in the sample efficiency of the approach, and this sample efficiency allows for building more complex more complex architectures that can be used to process the input time series. The common downside of these two approaches, at least in their standard implementations, is that they both neglect the dependencies that might exist among the time series. There are few methods that have been used in the literature to deal with this beyond the graph representations we will be talking about later. And the naive option, the one that the straightforward thing to do would be to consider the input collection of time series as a single very large multivariate time series, but this clearly has severe scalability issues, since this clearly suffers from the curse of dimensionality, so it results in high sample complexity and poor computational scalability. We can instead consider models that operate on sets of time series, keeping the parameters of the model shared among these time series. And an example of this is like attention-based architectures, like transformers, where in this case, attention would be computed with respect to the spatial dimension rather than the temporal axis. And this approach can work pretty well, but as you know, like if you are familiar with also like with the static graphs, we know that using the transformers to process these kind of data can work pretty well, but clearly the downside is that we are not exploiting any prior on the structure of the dependencies and also on the sparsity of this dependency structure. There are also other methods that have been used in the literature that, for instance, rely on dimensionality reduction. And here the idea is that we can extract some shared latent factors from this large collection of time series and use these factors to condition a global model. And these can work well if data are low rank in certain application. But the downside of this is that we are losing the local fine-grained information, which instead, as we will see, is captured very well by the graph-based approach. And of course, also these approaches in cases of like very large data set, very large collections, can suffer from the same scalability issues of the other approaches. Now we can start talking about these graph-based representations. So as anticipated, the idea is to use a graph to represent the functional dependencies among the time series and use this graph as an inductive bias for our learning model. We can use the graph adjacency matrix to capture to model these dependencies, and adjacency matrix which can be both asymmetric and dynamic, so it can vary with the t, so with at each time step. Together with the adjacency matrix, we can also have edge attributes, which can be dynamic on their own, and that can be both categorical and numerical. Finally, we can go back to the traffic example, and here again we will have that the structure, so the graph, the adjacency matrix can be extracted from the structure of the road network, and you can have like attributes or weights associated to the edges also to encode the road distance. And here in this case, a dynamic topology can help, for instance, for taking into account modifications in the traffic network, in the structure of the traffic network. This is a sort of summary of all the information that we have available at each time step. So we have our target time series together with exogenous variables that can be both dynamic and static, plus the relational information that we just added to the setting. So now the idea is to use this relational side information to condition our predictors, our forecasting architecture, and these relationships, as we will see, can act as a regularization to localize the predictions with respect to each node, and in particular, these can be used to prune any spurious correlations that might be the result of not taking this structure into account. Furthermore, this approach is far more scalable than standard multivariate models because, again, we can keep the parameters of the model shared among the time series we are processing. In fact, we can use these kind of architectures to forecast and to process any subset of the correlated time series. In particular, the kind of graph neural networks that have been developed to process these data are called spatiotemporal graph neural networks, to refer to the fact that propagation in these models happens across both time and space. And in particular, we will focus on those models based on the message passing framework. And we will do that by considering this template architecture where we have, which is composed by an encoder, which simply encodes the observations, each observation independently at each time step and node. And the encoder is then followed by a stack of spatiotemporal message passing layer, which is the only components of the architecture where the propagation through time and space happens. The representations extracted by the spatiotemporal message passing blocks can then be mapped to predictions by a decoding block, a decoder block. We can look at more finer details of this, and you see that the processing here happens at the level of the single time step again and single node for what concern the encoder. The resulting sequence of observation is then processed by the spatiotemporal message passing layers. The decoder, again, will then be operating at the level of the single node and time step to map these representations to prediction. We can have then several implementations of these spatiotemporal message passing blocks, and we can see this as a sort of generalization of standard message passing layers, where instead of having like static representations associated to each node, here we have sequences of representations. So what we will need to do is to modify the standard operators that compose a message passing architecture so that they can process sequences. Clearly, there are many possible designs that exist to do this, and that can be somehow matched with the requirements that we have for each specific application. So the next step will be that of characterizing the possible design paradigms for these spatiotemporal blocks, but this would be a good moment for asking any questions or clarify any doubt before moving on. So if you have any, feel free to use the chat or just unmute yourself and ask directly. Okay. No questions, but yeah, anyway, if you feel like some step of the discussion is not clear, feel free to use the chat and we will keep an eye on it. Okay, so there are, as I was saying, there are several, okay, we have a question. Yeah, go ahead.
Sorry, they can't unmute themselves. So
Okay,
do you want to
okay.
read out the question? Yeah.
Yeah. Okay, so regarding correlation, it's possible to use STGNN multivariate that have signals. Okay, so I think you are referring to irregular time series. This is a good question, and there are methods that can be used to model these kind of irregular observations over time and space, and we will touch on them in the second part when we will be talking about dealing with missing data. But yeah, there are methods to do that. Then the other question is the encoder-decoder also design choice? And yes, it is. You have different operators that you could use. In practice, in many cases, since these are just, again, a first encoding, a first transformation, and later on just a readout, these are usually implemented with standard MLPs. But yeah, in principle, you can use whatever, basically. Okay. So as I was saying, there are several methods, is it similar? Okay, is it similar to embeddings in transformers? Do we encode positional information too? We will talk about this in a moment. There is something similar to this that is actually used often in this kind of models, but we will arrive to that point. So for what concerns the different designs, we can distinguish between time and space models. And here in these kind of models, the temporal and spatial processing cannot be factorized into separate steps, so they happen jointly. We then have time and space models, which instead, as the name suggests, they factorize the processing of the temporal and spatial dimensions in two separate steps. And finally, we have the space then time approach, which is basically the time then space in reverse order. For the time and space, as I was anticipating here, it is that in this model, the propagation of representation through time and space happens in a way that that means that the resulting model architecture, this processing cannot be factorized into separate stages. And there are several ways of implementing these architectures. For instance, one standard way is to integrate message passing into sequence modeling architectures. We will see some examples of this. And the other approach is instead to use sequence modeling operators directly to compute messages in a message passing layer. And finally, there are also product graph representations, which are basically a way of getting a static graph representation from these collections of time series so that we can use standard message passing operators on that. So one standard example, and actually also from a chronological perspective, this is probably, at least to the best of our knowledge, the first model that has been introduced to do this. We can start from looking at a standard GRU cell, so looking at a standard gated recurrent neural network. And you can see that here, clearly each time series is processed independently from the others. We can easily get the spatiotemporal graph neural network version of this by implementing each gate of the recurrent cell by using message passing. This is also very similar to the first kind of graph neural networks that have been also used to process static graph data, but in this case, at each step, at each update of the cell states, we perform message passing at a different time step. So we use this network to update the states of the cell at each time step by reading information at neighbors. And these kind of time and space models are known as graph convolutional recurrent neural networks. And there have been many versions of this, in particular, many different architectures that have been trying to implement this by using different message passing blocks. In particular, one very popular architecture to do this is known as the diffusion convolutional recurrent neural network, which is basically a GCNN, where the message passing operators are implemented by this bidirectional diffusion convolution, where basically the idea is to have different weights for incoming and outgoing edges. And this was one of the first models that have been used to process time series, and has led to many follow-up, and it's still quite popular and quite effective. The second example is spatiotemporal convolutional networks, where here what we are doing is just alternating temporal convolutional filters with spatial convolutions, so with convolutions on the graph. So basically here what you are doing is applying standard temporal convolution at each node separately. And again, you can use any kind of temporal convolutional filter that you want. This is going to be a 1D convolutional filter. And then follow this with a step of message passing. By stacking many of this layer, you get an architecture where the receptive field will get larger at each layer with respect to both time and space. In particular, there's this STGCN, which has been the first architecture of this type to be introduced in the literature. And here, basically, the blocks are stacks of gated temporal convolutions with polynomial graph filters. And similarly to the recurrent STGNNs, also for these kind of models, there have been many different implementations. In particular, there is one model which is called Graph WaveNet that has been out since 2019 and is still very popular and still performs very well in benchmarks. And the idea is to basically use more advanced convolutional operators, also including dilation, to increase the receptive field of the model faster. The third example of a time and space model is those models that use sequence modeling operators to compute messages. And here, this one is a simple example where the messages are computed by using a TCN again. In this case, basically what will you be doing is to just concatenate the time series, so the sequence of observations at the two neighboring nodes, and then apply a convolutional filter on the resulting sequence. Clearly, you can use whatever sequence modeling operator that you want. And for instance, there are many examples of these kind of architectures that use attention operators. And in this case, this will be a cross attention, since you will be computing attention between sequences of two different nodes. We then have the product graph representations, and these models, these representations come from the simple observation that you can see the temporal dimension as a line graph and combine in some way. I mean, there are several ways that one could consider, combine this temporal graph with a spatial graph. And then again, process the resulting representation using a standard message passing net. For instance, you can consider a standard Cartesian product, where basically here each node will be, each node at each time step will be connected to its neighbors and to itself at the previous time step. There are also other ways of wiring this graph that you might use, like the Kronecker product. And in this case, the idea is to connect each node to its neighbors at the previous time step. You can also come up with many different methods of wiring this graph. And actually, I think this is a direction where further studies would be needed also to understand the properties of these product graph representations. We can then see the time and space approach, and this one is very simple also to understand. Also, the resulting models are very simple to build, and the idea here is to just embed each sequence separately into a vector representation and then perform message passing on the resulting graph. And the advantage here is that This is very easy to implement and also computationally efficient, because at the training time, again, you're not performing message passing at each time step, but only at the last one. And we can also reuse all of the operators that we already know to process sequences and graphs. The downside of this is that this two-step procedure might introduce a very serious information bottleneck. And as you know, this can make some of the issues that we commonly have on graphs, such as over-smoothing and over-squashing, even more serious. Like, it could make very difficult to propagate long-range information across space and time. And also, since you are performing message passing only with respect to a single graph representation, this would also make it more difficult to account for changes in the topologies and also for dynamic edge attributes. Then we have the space then time approach, which again, as anticipated, is basically the other way around. Here you are performing message passing at each time step separately, and then you are encoding the sequence of representations with a sequence model. Here, these approaches have been used quite often in the literature, but actually they still might have this kind of bottlenecks and this kind of factorized processing that might make it more difficult to propagate information, and they do not enjoy the same computational advantages of time and space models since you are computing message passing for each single time step. So now, I see maybe there's one question. Okay, yeah, there are also, okay, the question is about if we have other options to model the temporal dimension rather than using a line graph. Yeah, for sure. Like, I think you can consider any representation that you want, as long as you take care of somehow preserving the structure of the data. Also, one thing that I've not said is that when also you perform message passing on that kind of graph, you should take care of considering that the temporal and spatial edges have a very different meaning. Like, for instance, you could use different weights to process the different messages or things like that. But yeah, in principle, I think it's the general idea is that of using these static graph representations to process this data. And I think the optimal way of, the optimal representation that one might use is kind of an open question, or rather, using different representations might have different properties that might align well or not with your problem. Is there a method that use time then space then mixed? Well, you can do all sort of wild things. The problem is that with the usual time then space approach, usually what happens is that after you have encoded the temporal information, after that you have a static representation, right? Because you perform message passing only with the representation extracted by the encoder. So you have time series going in the first step, so in the time step, and then you have a graph coming out, which is later on processed. Of course, you can imagine something that works slightly different. Maybe you can add some kind of skip connections or whatever, but yeah. Also, I think these things that you say, like time and space that's mixed, is somehow similar to the time and space models that I was talking about when we were talking about the convolutional approach. In that case, they work exactly like this. So they interleave these the temporal and spatial filters to progressively increase the receptive field. Okay, then I think we can move on, and then later on we can go back. We can answer further questions. So this globality and locality thing I've been talking about quite a bit in the presentation plays a big role also in STGNNs. So STGNNs, at least in their standard implementation with this template that we have been talking about, they are global models. So they can handle arbitrary node sets, so they are inductive models, and they can use the dependency structures to provide further conditioning on the predictions, on the forecasts. However, this further conditioning might not be enough, and the model can struggle in modeling all the heterogeneous dynamics that might be present in the time series collection. And as a result, the model might need very long observation windows and a very high model capacity in order to account for all of these different heterogeneous dynamics that might be present. One way around this has been that the literature has somehow followed is to consider hybrid global and local architectures. One straightforward way of implementing an hybrid architecture would be to just, for example, like looking again at our template architecture, to turn some components of this architecture into local. For instance, you could make the encoder and decoder have parameters that are specific to the time series that will be processed there. Clearly, the resulting models would be able to capture these local effects much more easily. You can see this as kind of similar to using like a backbone model and have some layers that are fine-tuned or that are specific to the kind of data that you want to process there. And of course, the downside is that if you want to process many time series using this approach, this would result in a very large number of local parameters, depending on how these encoder and decoder blocks are implemented. One way to amortize this cost is to simply consider node embeddings, which are just vectors of learnable parameters that can be associated to each node. And this slightly goes back to the previous question, and you can see this kind of node embeddings as a sort of learnable positional encodings. But what they are doing here actually is not encoding the position of the node in the graph, but actually taking care of modeling the local components, of modeling the specific characteristic of each time series. These learnable components, these learnable vectors can be fed into the encoder and decoder, and as I was saying, they amortize the learning of these local time series specific processing blocks, allowing for keeping most of the model's parameters shared. Clearly, we still have the downside of having a number of learnable parameters that in this way scales linearly with the number of time series that we are processing. And so there are intermediate solutions that one might consider, such as learning embeddings for clusters of time series rather than for each single sequence. One other issue that is very important to consider here is that when we move to hybrid architecture, the resulting model is not inductive anymore. So this might sound as a downside, and actually is. So you definitely lose some flexibility, but in practice, you also gain something in transfer learning scenarios. So in those scenarios where you have some data from the target domain that you can use to fine-tune your model. In particular, having an hybrid architecture allows for keeping the shared parameters of the model shared, keeping most of the global components of the model shared and just fine-tune the local parts. In this case, just fine-tune the node embeddings. And in particular, has been shown in the literature that regularizing these node embeddings can facilitate this transfer learning procedure even further. We can start and we can have a look at some empirical results. So these four are very popular benchmarks for correlated time series forecasting. In the uppermost part of the table here, we have some baselines, some reference architecture that have been developed by using the template that we just saw. In particular, we have these GCNNs that are used, that are basically time and space models. And then we also have different implementations of time and space models. And then we have also 3 architectures from the state of the art. So we can see that when we add these local embeddings, so for the baselines, when we make these models hybrid, so when we introduce some part that is modeling the characteristic of each time series separately, we see that performance can improve by a wide margin. So much so that with these very simple architectures, in many cases, you are able to match the performance of much more complex state-of-the-art models. Also much deeper with many more parameters. We can then have a look at some transfer learning results. So here what we did basically was taking 4 data from 4 different traffic networks. We trained a model on 3 of these networks and then performed the transfer step on the 4th one. The first observation is that the fine-tuned model, so the models after transfer learning, perform much better than the zero-shot inductive model. This is somehow to be expected, and we might also expect this gap to be narrower if we use more data to train the model. But the other very interesting thing that we can see is that the performance of the hybrid architecture, where just the local components are fine-tuned, are fit on the new data, are much better than those of the fine-tuned global model. In particular, these variational and clustering thing are regularizations that have been studied in the literature in this paper cited here. And by using these regularizations, performance in transfer can be improved even further. So now we have reached the end of the first part. We formalized the problem of processing a correlated time series, and we show how we can use graph representations for modeling the dependencies among them. We discussed the forecasting problem and this important distinction between global and local deep learning models for time series, which is a crucial aspect of the whole thing. And we then saw approaches to building spatiotemporal graph neural networks and the associated trade-offs. Before discussing the challenges, we will look at software implementations of the above. In particular, Ivan will be presenting a tutorial of a library that we developed. But yeah, before that, we can answer some questions and have a short 5 minutes break. Would be interesting to analyze the causes of the local behavior. Yeah, would definitely be interesting. There are different things that you can do. One analysis that, for instance, we did in this paper here was to cluster the node embeddings well, actually the clustering was done end-to-end. And then we looked at the resulting time series clusters, and actually you could see that the corresponding time series were quite different. In particular, we used a data set of like load consumption, and there it was easy to see that those time series had very different behaviors. For example, like very different consumption patterns in the same days of the week. But yeah, I think this is all. You could probably also do something which is more fine-grained if you also if you use some way of representing some local components which is more interpretable. But I think this is kind of an open question. But yeah, you can definitely try to use this somehow to analyze the different behaviors. The other question is, so the static graph after time series is encoded to a graph. Is it a universal problem in both local and global models? Can it be solved with dynamic autoregressive context? So, okay, the fact that the time series are collapsed into a static graph representation is typical of time then space models. This does not happen in time and space approaches, as we saw before, like for instance with the recurrent graph convolutional networks. There, the representation is not collapsed. But this thing of having these global and local aspects, it's orthogonal to all models. I think it's even orthogonal to graph-based approaches. It does play an important role here, since you want to take these dependencies among time series into account, but this is something orthogonal to the specific architecture that you are using. Could you comment on which approach, time and space, time then space, space then time, is commonly used for traffic monitoring? Well, these, again, there are many architectures that use many different, that are wired in many different ways. So the literature is very, very rich in this regard, and there are also surveys that try to classify all of these different approaches. I'd say the time and space approach is the one that is most commonly used, but this also depends on the kind of constraints that you have. Particularly if you have computational constraints, the time then space approach works pretty well. But I think the fact that that approach can work pretty well also depends on the kind of data, right? So if you really need to model a longer range interaction, in that case, a time then space approach might not be enough. My suggestion, and later on we will try to come up with some guidelines, is that you can definitely start from using a time then space as a first try, since again it's much easier to train, much more scalable, and if that gives you good results. And we will also talk about quantifying, well, saying what good results mean. Then it's fine. It's actually much more easy to use. Is there any loss function that takes into account the variance and error, for STGNN? Well, I think you are referring to, well, again, you can fit these models using basically any kind of error function that you want. For instance, if you want to take the variance into account, and by taking the variance into account, I mean quantifying the variance, you can train a probabilistic model. As I was saying, this is not covered by the tutorial. We are just considering point predictors. for simplicity, but there are many resources on how to build probabilistic time series forecasting models, and I'd say that this is pretty much orthogonal to the discussion we are having here. But yeah, for sure, there are methods that you can use to quantify uncertainty and yeah. Okay, so I think we can have the short 5 minutes break, and no problem, no problem, nothing to be sorry about. We will have the 5 minutes break, and we will be back with the tutorial at yeah, 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 in 5 minutes.
Okay, so hello everyone. We can continue with the second part. So now we had the tutorial, or actually, I think we skipped the slide with the tutorial information.
Yeah. You can share
Let
it
me.
back there.
Okay, sorry.
Okay. Okay. Just click here.
Okay, are you okay?
Okay.
Okay, yeah, sorry. So in this demo, in this part, we will see how we can actually build spatiotemporal GNNs. And we will use for this purpose an open source library that we developed in our lab, which is called Torch Spatiotemporal. You have all the links here. So we have the documentation of this website and the GitHub repo here. You have all the links in the PDF online, as well as the QR code. So I will leave it here for a couple of seconds if you wanna open it from the QR code. Yeah, so we will move back to okay, to the Google Chrome. Okay.
Yeah. Okay.
Okay. So as I was saying, now we will start by let me attach to the okay. So in this notebook, what we will see is to explore all the functionalities that are available in TSL, so in Torch Spatiotemporal, which is a library relying on PyTorch and PyTorch Geometric and also PyTorch Lightning to ease all the research, or in general to okay, sorry. To foster also research and accelerate research on spatiotemporal data processing using graph neural networks. So let's start by installing all the necessary computation, necessary dependencies. So here we are simply installing the environment. What I suggest you is to have an environment in which you install your torch, your favorite torch and PyTorch version, and then install Torch Spatiotemporal afterwards, and it will install all the other dependencies. So now at the moment here we are using Torch version 2.5.1. Okay, let's just, this is just, let's say, routine code just to import everything we will need and to have a look at which version of these dependencies we are using now. In the meantime, let me just briefly introduce the library. So TSL is not just a collection of layers, let's say. It's not just if you want something which is like easily plug and play and have all the possible implementations of STGNNs online, it might not be the right library. What instead wanted to have inside is to cover entirely the pipeline from the data acquisition to the downstream task. So we start by loading a given dataset, and on the dataset we can apply all the usual pre-processing stuff that it's needed when we want to do forecasting, for instance, like scaling and normalization of the data, all the tools for resampling the data according to the given sampling rate we have, and to cluster data. We have a strong focus also on data coming from real world. So all the real time series where each observation is associated with a specific time step in the real life. Also tools to handle missing data and other irregularities, and we will see something more in the second part of the tutorial. And then, of course, we have all the parts about the modeling and inference, such as all the layers that we might need and ways to build our own STGNN. So let's start by loading a dataset from the ones available in TSL. We have a wide array of datasets. We have some datasets on traffic forecasting, some datasets for air quality or energy analytics. Most of these datasets are usually are widely used benchmarks in research in the spatiotemporal data processing community. We will start by using MetRelay, which is the dataset that Andrea was showing before in the tables. It's a traffic dataset, so it contains data from 207 loop detectors in LA. The sampling rate is 5 minutes, and we have approximately 4 months of data. So we load the dataset simply as you, I think you are already used to with other libraries. So we import the datasets from the tsl.datasets, and we download it in a specific folder. And here we can see that we have approximately 34,000 time steps, which corresponds to the 5 minutes for 4 months. We have 207 nodes, so the loop detectors, and for each node we have just one channel, which is the detected speed. So the time series, each time series is univariate, although we have 207 of them. Okay, so let's print some statistics about this dataset, some information. So we know that the sampling rate is 5 minutes. We know that there are missing values, and approximately they are at 8% of the data. We can have, in principle, exogenous variables. So the dataset come with exogenous variables. And among these, we have a matrix that tells us the distance among these sensors. So this covariate here, dataset.covariates, it's a way to, let's say, it's a storage for all the information that we might need for our task, but that are not the target of our downstream task. So in this case, we have the distance between each of the nodes, which should be, in theory, the road distance from a node to each other. We can have a look at it. So here, what the matrix is storing is basically that from the node 0 to node 1 and until 9, we don't have a path, essentially. So the distance is infinity. While for instead 1 to 2, we have this distance in kilometers, if I'm not wrong. No, maybe it's less. Anyway, now we can print also the dataset, how the dataset looks like. So here we have the nodes. These are the nodes ID. We have just one channel. And for each of these nodes, we have an observation every 5 minutes. So as I was saying before. So we start at March, and these are the readings for each of the sensors. Okay, fine. How we can build a graph out of this, because what we have now, these are the only information we have. So the distance between sensors and the data that we have. We have different ways in which we can basically build a graph when we don't have, let's say, a given ground truth graph. We will see later on in the tutorial more complex way to build a new graph. But here, what we will do is essentially to compute a similarity score between nodes given starting from their distance. We will use a Gaussian kernel based on the distance, just to convert the distance in some measure of similarity. So here, the closer are the nodes, the higher will be the score. So before the diagonal was 0, now it's 1. Okay, This is a standard way, let's say, to build a graph based on the distance. It has been used in several works. Now let's use this method instead, which is from here. What essentially we did is to get a similarity score out of the distance using this function. This is let's say it's embedded in the dataset. So each dataset can implement its own similarity methods, and we have some default one. While this get connectivity instead applies all the usually done post computation to post processing to this similarity matrix to make it a real adjacency matrix. So now we want to say, let's threshold the data. So all the data that are below 0.1, we consider them as 0, so no edge between 2 points. We remove self-loops. We normalize the weights on a given axis. So either the, let's say, the incoming edges or outgoing edges. And we want the layout to be edge index. So this is a very PyTorch geometric language, let's say. So here the edge index is simply a list of edges, which is then stored in a tensor. We can have a look at it. So we have this number of edges, so 1,500 more or less, with edge weights. So this is a weighted adjacency matrix. Here we have some operation just to convert it back to a matrix and to have also some the sparse to check that the sparse weights of this matrix are still the same edge weight as before. Okay. Now, let's say that from now, what we had is a dataset which is still not in PyTorch. It's mainly using NumPy and Pandas. And it's, let's say, a more user-friendly view of the dataset, and we can compute and do our standard analysis on that. But then when it comes to training a model and feeding this data to a neural model, we have to switch to the PyTorch interface. And we have this spatiotemporal dataset that basically comes in our help. And here what we do is to pass to this dataset a target variable. So it wants to know what is the goal of our task, basically, what we want to predict in case of forecasting, the connectivity matrix, any covariate or exogenous variables if we have them. So Andrea was mentioning, for instance, the encoding of the time of the day that might be used here. At the moment, in this example, we don't have any, but you can add them easily. The mask telling if data is available or not. And then we have these parameters here, window, horizon, and stride, that decides how this dataset is then split into windows, which are then fed in our model. So for those who are not familiar with the sliding window approach, what usually is done when we have a long time series is to split it in windows and feeding the model with just small windows of data, and then predict, let's say, what we k steps ahead. In this case, the steps ahead are defined with the horizon parameter. The length of the look back window is defined with the window parameter, and then we have a stride parameter that defines how many how many time steps are there between a sample and the other. Okay. Here you have all the let's say all the parameters that you can pass to these class and the effect that they will have on your time series. So if there are questions, please just write them to the channel. I will have a look to the channel sometimes, from time to time, and so I can be. Oh, okay, I'm sorry. It was a previous question. Okay. Okay, so this dataset, once we create this dataset, now we basically have splitted the long time series into smaller time series, and all of these are now different samples of our dataset. So now we have this number of samples here, and still we have the nodes and channels as before. Each of the sample will have 12 time steps inside. And we can actually have a look at it. So yes, we have 12 time steps and still the same number of nodes and features. Okay, we can go, I mean, here we have this, okay, the torch dataset. You can access the different, torch dataset is the dataset that we just built, and you can access the any samples as if it was, as if it's a list. So in this case, we are getting the first sample in the list. And this data object that is returned is basically an extension of the torch geometric data object, but it's wrapped in our custom TSL data object. And here what we have is the, let's say we built upon the original data, and here we have two inner kind of dictionaries, let's say, or storage object in which we store all the inputs variable and all the targets variable. So here all the inputs are the ones that are given to the model, and the target are the one that instead we want as output. You don't have to specify all this information when you build your dataset. You have the maximum flexibility to edit all of this, but if you don't do it, the most common let's say procedure is adopted. So your time series is splitted, and when you pass your target, so the target time series becomes both the input, and it's named as the X, and the target, and it's named as the Y. Okay. Now, yeah, here we can see what the input is containing. So the X, the index, and the weights of the index. So basically, the input to our model are the same that we have seen in the tutorial. So the X and the adjacency metrics. And the target is just the Y. So we are not, again, we are not predicting a graphs as output, but just time series. Graphs is just a mean that we use to process for processing in our input. Okay. We can, in this case, we can see if we have a mask, and we have it. So the mask is telling if data is missing or not. In this case, all the data that we are seeing are not missing. And we can see if there are transforms. So the transforms here are the scalars that we usually use to scale the data. So like for normalization or applying the min-max scalar, but we will see them very soon. Okay, these are other information. I can skip them to, I mean, you can have, this tutorial has much more information just to try to explain all the steps you might be interested in. But the core, we can skip some of them to do the core part. So an important thing is that the batching of the dataset is done very efficiently in the model, and you can access actually a batch of data as if it's a list, as I said before. So here we are getting the first 5 steps, the first 5 samples in the dataset, and so they are batched in a single object. The advantage of this approach is that it comes when we are dealing with static graphs. So we have the time series, let's say that the connection, the relationships among the time series are not changing or evolving over time. So we can assume that we have a single graph. And so in this case, we can have this advanced batching where it's basically we are stacking the time series, but we are not stacking the edges. And so the graph is the same for all of them. Okay, In this part here, we are basically splitting the data set into training, validation, and test, and we are fitting our standard scaler. So the ones that basically is removing the mean and divided by the unit variance, the variance. Okay. When we call actually dm dot setup, we are actually fitting all this information. This DM here, it's this Spatiotemporal data module. For those who are familiar with PyTorch Lightning, is an instance of the PyTorch Lightning data module. Okay, now let's go directly to the model part. So, as customary in all these libraries, we have all the neural network part inside the submodule TSL points NN. Here we have a collection of different layers that can be used, blocks, which are, let's say, implements a logic which is a bit more complex than layers, so such as encoders or decoders for our model. And we have also some models that can be already used. Now, for this tutorial, we will design a custom STGNN, and this will be done by following the time-then-space paradigm. So what we want to do is to embed all the temporal information in a single vector. So we end up with an attributed graph, and then we do the message passing on this single graph. We will also make use of node embeddings, so the parameters which are specific of each node, and this will make our STGNN a global local model. So let's have a look at I hope I executed all the important cells. So this is the model, the time-then-space model. So here we have the node embedding tables, which has a smaller size with respect to the hidden size we are using. We will have the encoding step. As we said before, it's just a feature encoding step. So this is takes as input a single time step and returns a single time step. It's applied pointwise. Then we will have the time part, which is in this case a GRU, a GRU. And then we will take only the last state of this GRU, so the encoding of the time series. And for the spatial part, we will use the diffusion convolution, which is the operator that is used also in the diffusion convolution recurrent neural network, and the CNN. And we will, in the end, have this single vector for each node, and we will have the decoding part, which is done by an MLP. So the logic, it's here. It's the one that I just mentioned. So we can go ahead. We can make our own by changing the number of layers. For instance, we can say 2 RNN layers here. We can increase the hidden size and embedding size and the number of spatial message passing layers. Okay, let's have a look at the model now. This is our model, and this is the number of parameters that we have at the moment. I also want to show you how the data looks like for our input. So what we are giving as input to the model? Well, first of all, this is what the model see for a time series. So let's say we are at the node 0, at sample 0, and these are the 12 time steps we are giving as input to the model, and we want to predict the next 12 in this case. And this is what a single, let's say, a local univariate model will usually see. So the time series of a node as input and its output. What instead we can do, thanks to the graph processing, is to also have as input let's say the set of the time series of the neighbors of the node. So here we have 11 nodes, so maybe it's not that easy to see something that can be helpful for the prediction, but what can be, what's the rationale behind it is that in this time series, using this time series to forecast this signal on the right, it's actually it helps, it has improvements with respect to forecasting the signal only using the signal on the left. This value on the left hand side are normalized, as you can see from the scale, which is not the same for the target in this case, but for convenience we also plot the scaled target here. So there is a question. So in the first part of the tutorial, we were discussing that STGNN for traffic modeling, such as DCRNN, are time and space models. Here we implement the time then space model. Is the result the same? Please correct me if I misunderstood. So these are different approaches, different paradigms. So DCRNN is indeed a time and space model. As we briefly mentioned before, but we will have a deeper discussion right after the notebook. A time then space model is faster, it's more scalable, and so this is also why we chose to have this one in this demo, also for efficiency purposes. But also the performance of these approaches are not that bad as one might think compared to other time and space models. So in the end, we will see. I mean, we are not looking at something which is, let's say, a very stupid network. It's something that theoretically can work very, very well. Okay. Okay, we now go to the training part. We have in this TSL.engines, we have a predictor module, which is a lightning module that can be used to ease all the let's say the burden, which is that we usually have to do to define the training loop and validation loop and all this and the evaluation pipeline in general. We can import the metrics that we define still in our library, and that are usually the metrics that are used in traffic forecasting, in forecasting in general. In the meantime, okay, I'm starting the training now. We won't do a very deep training. It's just to see also in this case that let's say that the burden of time then space model is not that that big compared to other time series forecasting methods. So here what the library is saying is that we are giving a input to this model, the x, so the input, the edge index, and the weights of the edges. We can have a look at what's happening during training now. So this is the train loss. So the model is learning something. But yeah, I invite you, if you are interested, to maybe tune some hyperparameters here and let's say and train your, let's say, your own STGNN on this example. For the sake of the tutorial is basically everything. It's I think we can simply stop here the training and just do the evaluation part just to see what happens in the end. So this is the we are loading let's say the best model, which of course is not I mean a fully trained model at the moment, and we are testing it on the test on the same splits that are used usually in publications. And here we can see the results. So this test MAE is the MAE is the absolute error in the entire horizon. This at 15 means after 15 timestamps, and after after 15 minutes, so after three timestamps in the future, while at 60 is after 1 hour, so at 12 timestamps in the future. And all these metrics are here because we define them here. You can have your own. You can monitor whatever you want by changing or the metrics here. Okay, so this is pretty much it. You have the tutorial. It's this demo is available in the slides and also on the website of the tutorial. The library is online. You have it on GitHub, and read the docs. If there are questions, I'm happy to take questions on this part. If there are not questions, I will move to the second part of the tutorial. Okay. So, which one? This one?
Yeah, that.
Okay.
Okay. No, here.
Okay. Okay. So I hope you are still here with me. In this second part of the tutorial, we will have a look at the challenges that are inherent to this problem setting. So we will have a look at 4 challenges. So the first one is on scalability. So how we can deal with large collections of time series. So how we can process the data when we have lots of them. A second problem that also came in the questions before, so what to do when we have missing observations or misaligned observations in our time series. And then Daniele will cover the latent graph learning part, so what to do when the underlying graph is not known, so how we can learn the dependencies that are existing between the time series. And also how we can evaluate these graph-based models, how we can understand if a model is optimal or not. So let's start with the scalability part. Scalability is actually a feature, right? Because in using graphs, what we can achieve is to have a single inductive model, so a global model, while still we are conditioning on related time series in a sparse fashion. So we are not giving as input to the model the entire set of time series, or just one of them, but we are using the ones that we think are the most relevant for the prediction of the target time series. And in doing so, we reduce the cost of the usual operation of considering all the other time series from being quadratic on the number of time series to be instead linear of the number of these edges. So the dependencies that we found in the time series. But scalability can also be an issue here because we have data that, as the name suggests, are spanning the 2 dimensions. The first one being the spatial dimension, so the number of time series that we have, but the other one being the time dimension, so the number of time steps that we have in each time series. So in real-world applications, it's not that uncommon to deal with high-frequency time series and also with large-scale time series. So this is, for instance, the example in smart cities, like traffic forecasting or environmental monitoring. For instance, if we want to monitor the air quality, the quality of the air in open environments. Or this can also be the case in finance, where we have different prices at the level of seconds or even lower. for a large amount of in this case, of stocks of entities in general. So usually the problem is that we have a large amount of data and we want to process them all together. And this is particularly true when we want to account for the long range independencies that might exist either in time or in space or in both of them. So for instance, if we want to capture something which is very far in time and space. Now, let's have a look at what's the actual computational complexity of STGNNs. If we consider a time and space model, a general formulation, so there are very different implementations of time and space models, but in general, what they do is that they need some node-wise temporal processing, and also they have a spatial processing that scales usually with the number of time steps. So if we consider, for instance, a recurrent neural network, a graph-based recurrent neural network, at each time step we do, in this case, L layer of message passing. So what happens is that then we scale by let's say that by we need to do the number of message passing operations times the number of the time steps as input. So the first step toward improving the scalability is given by the time-dense space model, in which instead only temporal processing is still done node-wise, but then we just have to do the message passing on a single graph. So on a this is let's say as if we had just a single timestamp. And in this case, we have an additive computational complexity, let's say, with respect to edges and time steps instead of multiplicative. And as we also have seen before, this is not an advantage that space then time models have instead. Okay, this is quite a good achievement, but it might not be enough when we have very large graphs or very long range dependencies. So what else can be done? A possible approach, a possible solution could be to reduce the computational complexity by considering some subgraphs of the full network. So this can be done, for instance, by selecting a subset of target nodes and then just considering the ego graph of the induced subgraph on this subset of nodes up to a given order of the neighborhood, and then just do the training on this subset. Another option could be to rewire the graph to reduce the number of edges, since we are now not scaling with the number of nodes, but the edges. We can have some further sparsification over there. All these methods are actually borrowed from the static graph community. So we have some example, for instance, Graph Sage or a Drop Edge or many other. The problem is that the subsampling might break long-range dependencies if we have. So if we consider a very small k, then we might actually lose some important dependency. Instead, if we use a large k, we might instead end up with the original graph or something similar. Another disadvantage is that the learning signal may be noisy, so we might have problems in optimizing our network. Another option instead is to sorry. Okay, another option is to instead move part of the computation before training, so ahead of training. This actually helps us in removing all the burden, all the heavy lifting part in something that we need to do repeatedly during training. So a possible, let's say, an example is represented by Cini, which is this architecture that precomputes some representation of the neighbor of a node, and then allows to this allows us to sample the obtained features as if they were IID samples. These works have been done to reduce, let's say, to enable scalability on large static graphs. And a possible extension to instead the spatiotemporal setting is given by this other work, SGP, in which we also have a further pre-computation made over the time. So instead of, besides having the pre-computation of the node features, we also, let's say, the spatial neighborhood feature, we also have an encoding vector that tells us what has been the history of each node. This can be done through an ecostate network. This is done actually through an ecostate network in this work, which is basically a deep RNN which randomized weights. And then we can, after this encoding, we propagate these encodings to the graph using powers of a given graph shift operator, so a function of our adjacency metrics. And here we have the example of the architecture just to have a visual representation of it. So what happens is that the time series go inside this big recurrent network, and then gives us input our encoding, as output our a new encoding at each time step that it's propagated over space in a non-trainable fashion. Now we reduce the training step, the cost of the training step, which is now independent of the length of the window, the number of nodes, or the number of edges. The training step is now simply constant, basically, because we can sample these features from this newly constructed dataset as if they were IID. And also the performance are not actually bad, so they match the state of the art. But they have some downsides. The first one being the fact that we are now extracting more and more features. So the dimension of the vector which goes inside this MLP, so the downstream network, is now much bigger than the initial time series. And also it's more reliant on hyperparameter selection, as expected, because now many parts of the network are not trained. Finally, what else? Another option to reduce the computational complexity is to use some coarser grained representation of the input. So instead of using the time series at the initial sampling rate for in each processing, in each step of the processing, we can reduce this processing, this resolution, both in time and space, actually. And to do it in space, we can rely, for instance, on graph pooling, which are techniques to reduce the size of the graph by associating a subset of nodes to a super node in a new graph. So now what we can do is to reduce the number of operations that are needed to reach the same receptive field as the original graph with a deeper network. But also the downside is that we are introducing bottlenecks in propagation of information now. So for the first part on this challenge on the scalability, that's it. So if there are questions on this part, I'm happy to answer. I hope everything was clear. Okay, so I will move to the second challenge, which is dealing with missing data. Leaving just a couple of seconds for if there are some questions. Okay. So until now, we assume that we are dealing with complete sequences, so that at each time step and for each node, we have a valid observation. This is, of course, not the case in real-world applications, where usually we have missing data that are due to different reasons. It might be due to faults of the sensor that can be transient or permanent, so we can actually lose sensor somehow at a certain point. We might have asynchronicity among the time series, and this results in having missing values let's say, in a not synchronous way among the time series, or for any error in general. And the problem is that most of forecasting methods do not consider this problem. They assume to deal with complete sequences. So what we need to do now, we need a way to fill in these missing values, to reconstruct the missing data that we have in the input. The problem of time series imputation is precisely the problem of estimating the missing observations in a sequence of values. So here we can see we have the same figure as before, but now some values are missing, and what we added is an auxiliary binary variable, which is this mask m, which denotes if a value is missing or available. In the end, what we want to do is to provide an estimate for all those values for which the mask was 0 as input. There are different data types. We provide a taxonomy which is based on this conditional distribution. So on the distribution distribution of the mask conditioned on other values of the mask. The point missing case is let's say the similar to the missing completely at random case. So here what we are saying is that the probability of a point being missing is the same across all nodes and time step, and is basically associated with the Bernoulli with the same cost, the Bernoulli with the same constant to each node and timestamp. And this is something that usually models, let's say, the communication error that we might have in a remote sensor application. Instead, in the block missing, we have that this distribution is not independent from missing data at other nodes or time steps. So we might have a block of missing data if we, in the case of the temporal block missing. So here we might have, for instance, a fault that generates consecutive missing values. We might have spatial block missing if, for instance, we have a blackout in a region of a smart city, or a combination of them. When we have missing values, we need to make some adjustment when we optimize the parameters of our model. So here, what we want to do is to compute the loss only on the valid observations that we have. So here, this the loss function that we are using, for instance, the MSC, is then weighted by the mask just to say, okay, let's just take the values that are really available in our problem. And this loss is usually the one that is used for forecasting with missing values, or to compute our reconstruction loss on the data we have. When instead we do imputation, sometimes we might need to inject some missing to train our model or to do evaluation of our model. And so we mark some of the observations that we have as missing, and then in this way we obtain ground truth labels. And of course, these data cannot be used in the model to obtain the imputations. In deep learning literature, there are different approaches to tackle this problem. And one of the prominent approaches is to use autoregressive models. So for instance, RNNs. In this case, what happens is basically that we process our input sequence, and as soon as we find a missing values, we impute the missing values using the prediction coming from the recurrent neural network. So using the observation that we had before. So this is effective in exploiting all the past information that we have at a single node, and we can also account for future observation if we use, for instance, a bidirectional model. But if you look at this process, what you can easily imagine is that if we have a temporal sequence of missing values, here we are continuously updating, let's say, providing forecast for that value using prediction from the RNN. So we might have compounding of errors along the temporal block. And another downside is that this approach is struggling capturing nonlinear space and time dependencies that might be present in the data. So again, what we can do is to use the relational information that we have to condition the model. So instead of having a single model for each time series for the entire set of time series, we can have a model that can be applied to any time series and can take as input our graph to sparsify the relationship and dependencies in the data. An example of this is represented by green, where similarly to what we did for the graph convolutional RNN for forecasting, we integrate the graph processing into the autoregressive approach that we have just seen. So here, in general, what we do in these approaches is to model this distribution, so the probability of a datum given the entire sequence, into 3 independent steps. The first 2 being the information, getting the modeling the distribution, the condition of the information at the previous time step or subsequent time step. And this is what is done typically by a bidirectional RNN, which is the model we just saw before. What message passing allows us is to also consider related concurrent observations. And this is powerful, for instance, when we have long sequences of missing values in a given node, but we still have information at neighboring nodes. Imputation is usually done as a preprocessing step, as I said before, for a downstream task, for instance, forecasting. And this is often necessary and for the nature of the forecasting models that we have that expect complete sequences as input. And so the pipeline that usually is done is to impute this missing value and then proceed with the forecast afterwards. But this, of course, might introduce biases due to the errors in the imputations. Another use case instead is that of using an imputation model in place of a forecasting model. So we can also simulate we can imagine to have a longer sequence than the one that we have, but with full of or empty, let's say, from values, so full of missing values. In this case, we can adopt essentially also imputation methods that are not meant for this, but this is, of course, a workaround. So this performance might be also, the performance might be also poor due to the absence of values. So if these methods, the methods that we use are strongly relying on values, for instance, at the boundaries, this is not a good choice. What instead we can do is to take a more direct approach where we want to avoid at all this reconstruction step and directly deal with irregular observations. So in this case, what we do is to have a forecasting STGNN, which is tailored and thought to deal with values that might be incomplete. So here we have several benefits. The first one being that we now can learn directly how to leverage only the valid observations, so we don't need to impute or to carry on some estimates of the missing values that we have. And this is done precisely for the task downstream task that we have at hand. And also we avoid the computational burden that is usually that comes with the imputation processing in a preprocessing step. Now, besides imputation, another important topic that can be considered is that of virtual sensing, which is the practice of estimating unmeasured data states using the data in the model that we have. So if we have a set of nodes, we might be interested in knowing, okay, what will be the observation, the corresponding observation at a given node that I do not have in my data. And now here we can actually see the power of graphs in doing so, because we can exploit these relational dependencies to condition the estimates. This is actually what we do, to condition estimates on data that are close in some space, which can be inside, in this case, it's the center space, so that's the space where time series are. And thanks to the inductive property of message passing, we can handle new nodes and edges very easily. And this is also useful where in applications where desensing has a cost. Now, an application that we can see here, it's basically an example of using methods that are thought for just doing imputation to instead being applied to virtual sensing. So in this case, we are simply adding a fictitious node in our data and without any observation, and we see what happened when we want to reconstruct the to infer the corresponding time series. And this is done with an graph imputation model. And the results are not bad, so we can still recover something, as we can see from the figure. But of course, there are several assumptions that are needed. So we have we need a high degree of homogeneity between the sensors. We need to assume that we have a capability to actually reconstruct given neighbors using only neighbors and many more. So this concludes the part on the first two challenges. Before leaving the stage to Daniele, I'm here to answer any question. So if you have question on the scalability part or the missing data part, I'm happy to answer. Okay. I think that's it. So I will leave the floor to Daniele.
Okay, so hello everyone. I'm Daniele Zambon, despite the name probably that you see is still Andrea Cini. But so here we are. So I'm gonna now talk about this other problem related to latent graph learning. which stems from the fact that all that we have seen so far rely on the fact that we do have some relations that spans or connect our time series. But what if such information is not available? Of course, we can imagine scenarios where we have several time series, but no relations are given to us. Or, for example, we do have some time series or some relations, but we do not know all of them. Or other scenarios could also be that the information that is given to us is not trustworthy, so we cannot assume them to be reliable enough, so we want to learn them from data. So this, in fact, the possibility to learn relations from the data that we have, the time series that we have, is something that holds a potential to apply all that we have seen so far also to other scenarios. So, okay, I see another. Okay, no, sorry, this is just someone in the waiting room. I cannot add it anyways. So I will move on. So, okay, so I was saying learning these type of relations from data. So here we have seen that we see that we have some time series, and we want to deploy or devise a model that is able to extract some information in different ways. So what is central to this topic is the fact that in order to really rely on graph neural networks, we expect the graph that we extract from data to be in some sense sparse, so that we can rely on all the advantages that we have seen from the previous presentations on low computation, maybe scalability linear in the number of edges, and not having to scale quadratically in the number of nodes. This somehow can also serve as a sort of regularizers for our attention mechanisms, so that we can remove or drop several connections that we know or we find out that are not relevant to make our prediction better, and so focus on only the most relevant ones. And lastly, to introduce still this topic, I want to say that this graph extraction process can go under different terms in the literature. We may find the graph structure learning as the most used one, but other names can be appropriate as well. So in this case, I'm using latent graph learning because it's more informative for what we are doing here. So we have time series and we want to extract some relations that are in some sense before the time series or underneath them, that conditioned the realizations of the time series that we are seeing. So the first approach, probably is the simplest one, is that, okay, we have a set of time series, a collection of time series. We compute some sort of similarity between all pairs of time series. So, for example, we can take the Pearson correlation or a Granger causality from the time series. So in this sense, we construct, given the time series, a matrix that store all these similarities. And then, as I was saying, that we may be interested really in extracting something that is sparse, we may need to apply some sort of thresholding on top of this method. And yeah, so in this sense, first we decide what the similarity should be for us, and then from the graph that has been extracted, we use our STGNNs, or any graph-based model, actually. So another approach is that instead assumes that this graph is not something that we compute on top of our time series, but is actually something that has in some sense determined the realization of the time series that we have available. So this typically relies on some sort of assumption like that of a signal smoothness. So we say that or we assume that our signal is smooth in the sense that those time series that are more similar to each other is because they are more related to each other, and they are caused by a sort of some infrastructure that is underneath our time series. And by optimizing specific losses like the one that I'm showing here, which is basically a total variation of the signals that we have, we can try to recover the topology that in some sense determined our observations. Of course, the optimization of this type of losses also usually require that we, not necessarily this, but in general, this type of losses may require that we constrain. So here, of course, we are optimizing with respect to L in the left-hand side of the equation, or A on the right-hand side. On the left-hand side, we have a Laplacian. L has to be a Laplacian, so we need to constrain L, or the matrix L that we are optimizing or finding, to be indeed a matrix representing a Laplacian. Okay, so this actually is also interesting because in some sense it allows us to enforce some sort of sparsity as well within this optimization problem. So this family of approaches are commonly derived within the framework of graph signal processing, which have, of course, strong guarantees in this respect. What we are more concerned of in this presentation is that of task-oriented latent graph learning, where we are tackling this problem from a more, let me say, integrated way, where we are learning the relations in a way that our model in the end is performing best at the task we are considering. So we are optimizing the downstream task, and possibly we want to learn it end to end. So this is a difference from previous one, where we basically make a first step where we train the model, or we train the relations, or we learn the relations, and then we apply them, or we consider them along with the model that we are optimizing. So for this task-oriented latent graph learning, we have two main approaches, I'd say. The first one is a more direct one, where basically our adjacency matrix, so the graph that we are trying to learn, is modeled as a real matrix, n by n, where n is the number of nodes, and we're trying to optimize it in order to, of course, as I said, maximize the performance on the downstream task. The second one is a probabilistic approach of learning. Instead of, let me say, a deterministic matrix A, we are learning a random variable A distributed according to some distribution P of phi that we are modeling in some way that we'll see shortly. And often this is done mainly to allow our random variable A, our graph, to be natively a discrete object. Okay, so often we constrain P phi to produce random variables A, which are binary entities. So in this set 0, 1. So again, as I mentioned, the key challenge is probably here in this optimization framework of deep learning is to retrieve A in a way that this is in the end a sparse object that allows us to not only find few relations that are very relevant to the task at hand, but also to allow to maintain our computation sparse and therefore efficient. This is in particular not trivial in all those techniques that we use mainly nowadays, which are based on gradient-based optimization. So this direct approach, as I said, is not a probabilistic one, is as opposed to that, and where we have this our latent variable A that is here modeled in some ways as a function xi of some edge scores parameters phi. So here we can think of a phi as a starting point as a free parameters in floating parameters or real numbers, n by n matrix. And these numbers are completely free parameters, but then is the role of the function C to transform these parameters in some adjacency matrix, okay? This could be any functions, could be, for example, a sigmoid if we want to maintain this differentiability, or we may just threshold and say all positive numbers goes to 1 and the negative one goes to 0. So another thing is that now I said that phi could be a set or a matrix of free parameters. This is only one of the possibilities. Could be indeed an n by n matrix of parameters, but could also be itself a functions of other parameters, or for example, a function of the input itself. Okay, so in this case, I represented phi explicitly the dependency on some input data x and some other parameters tilde phi. So on top of this phi, we apply this xi function, which allows us to enforce different type of structures. Of course, the first that probably you are thinking of is making a binary matrix, but this is not only the only application. We can make, for example, a KNN graph, so that we allow to design or to construct graphs that have a bounded degree. So again, this could be, for example, for scalability issues, or some other more interesting or relevant for the application structures, for example, a tree, direct cyclic graph, or any other structure, as far as we have a way to enforce some structure. So another important or often used trick to model these edge scores, and this is intended to address the fact that these edge scores are in principle quadratic in the number of nodes, is to exploit some factorization of this phi. So in this case, we have other two matrices. This is ZS and ZT, so Z the source node, and ZT for the target nodes. So we can interpret these two matrices, which are smaller in the end in terms of number of parameters, as embeddings of the nodes, and by means of these embeddings and some either directly a dot product or some functions of the two, we can extract some parameters phi, and then in the end we see again produce an adjacency matrix A. So again, Z of t can be free parameters themselves, or once again functions of the input data. So there are several advantages of this approach, which are mainly on the fact that this is an easy to implement solution. The parameterization are really infinite, in the sense that all the layers that we have available in our deep learning framework are endless. Also because we have all this deep learning solution, they are supposed to work immediately once applied within the optimization tools that we have available. On the downsides, what we have is that as these are the free parameters are in the end real numbers, we all usually end up with n square computational complexity that, as you can imagine, does not scale well if we have a large number of time series that we want to consider altogether, especially during training, where we haven't reached a point where in the end the graph can be considered a sparse entity, but we are considering all possible connections that may exist. Then in that case, the computation, as you can imagine, is quadratic in the number of nodes. Indeed, one can, leave the parameters to be n squared and then apply some sparsification on top of that, but that sparsification is actually cutting all the connections that are zero, removing from the computational graph, and in that sense, the gradients cannot pass through that path. And so it's harder to train such type of parameterizations. And finally, so given the two shortcomings that I just mentioned, this makes the parameterization require some extra care to be able to allow to find what we are actually looking for. So the second family of models is a probabilistic, rely on a probabilistic approach, where, as I anticipated, is based on creating a parametric distribution P of phi, and this parametric distribution is for our adjacency matrix A. So there are different type of parameterization for this P of phi. Probably the most straightforward one is one on the left, where we assume that all edges of our graphs are independent between each other. So we can model each of these edges as a Bernoulli. And so in this sense, we have that Aij, so our variable or component of the adjacency matrix relating to the edge ij is simply a Bernoulli independent from all the others, whose parameter is given by the sigmoid of the free parameters or edge score phi ij. On the right-hand side, on the box on the right, we have another family of distribution. So as you can see, changing this distribution allows us to rely on certain assumptions or not, or force some structural priors on the graph that we are optimizing. And so in this box on the right, we have a distribution that forces graphs with a fixed degree, in this case k. So basically what we have is that for each node we have this list of edge scores, so phi i1 to phi in, and based on this we compute a softmax, so that this in some sense gives us the parameters of a categorical distribution, and then from this categorical distribution we can sample without replacement k nodes, and this will give us the neighborhood of node I. Indeed, this is a case without replacing and with exactly k nodes. Extension can be designed so that we may rely on assumptions such that we have at most k nodes, but yeah, so these are just two examples. Clearly here I talked as if phi were free parameters. Indeed, all the parameterizations that we have seen for the direct methods, such as the dependency on the input data or the possibility of factorizing phi as the inner product of the similarity of node embeddings, are still feasible and actually could be advisable in certain scenarios. And here on the bottom right, we also see a way to enforce some dependencies on top of these parameters free from the input data, so that we design a probability distribution that is conditioned on exogenous variables, for example, or the input x itself. So learning graph distribution may not be as simple as in the other case, and so we should pay some attention of what we are doing here. So basically we can construct several type of losses to optimize our distribution P of phi. So the first that we see on the left is basically averaging our predictions basing on ideally all possible realization A from the distribution P. So basically we are sampling an adjacency matrix, we are producing a prediction X hat, and then we compare, like for example, the mean squared error or the mean absolute error of that single prediction with respect to the actual observation that we have here denoted as X without the hat. So then we average all the losses that we can collect, and this will be our loss. On the right hand side instead we have a slightly different approach where basically we swept the expectation within the loss, so that basically we are making prediction for several A and then taking the average among all the prediction, and only then we assess the discrepancy with the realization that we have observed. So this seems actually similar, but just to let you know, there are some theoretical results for the right-hand side losses that are actually more would be more advisable in general to use that if you are really looking for a probabilistic model for our predictions. So here I just taken the expectation. This need not to be the expectation, could be other like functionals like the median and so on. So a more general approach in the spirit of a probabilistic model is probably to design a loss that is based or constructed as a discrepancy between the predictive distribution, so P of theta of X, so the distribution of our prediction X hat as determined by our latent variable A against the distribution of our observations. Okay, so this could be in the end this delta discrepancy or divergence could be the Kullback-Leibler, or could be, for example, the continuous rank probability score, could be an energy distance. So there are several of them. So this is just to say that there are different losses, but all these losses share one crucial or potential issue. That is the fact that if we wanted to optimize this directly with the gradient-based optimization, we need to take the gradient of these phi parameters, and these phi parameters are exactly the same parameters where we are integrating our loss. So are those that comes at the predicts of the expectation. Okay, so there are of course analytical solutions for certain scenarios, a certain loss, but many times these are unfeasible. And Monte Carlo approaches, which are also a lot used, may not be always feasible. Why? Because if we take a sample, for example, take the top left loss, if we take a sample A and then we compute the loss and we want to take the gradient with respect to P, there is no connection in the computational graph towards P. So for these reasons, there are some strategies to design Monte Carlo estimators. One approach relies on the reparametrization trick, which is basically a smart way to rewrite our distribution P phi of A as a function where the, or actually what we are rewriting is A itself as a function of our parameters phi in another component, another random variable, which has its own distribution. This is a sort of fixed, so that in the end, what we are, our optimization goes through or inside the function g towards the parameters phi, we leaving aside the probability distribution or the random variable epsilon here. So this in some sense decouples the randomness originating from epsilon from the parameters that are the ones that we want to learn. So this is a smart choice and used very much in practice. So in the end, you can see that basically the gradient with respect to phi can be ported inside the expectation with respect to the epsilon. And now this time the loss function depends on the parameters. So this is actually practical, and the only downside or the major downside that need to be pointed out is the fact that this is in the end a sort of needs to rely on a sort of continuous relaxation in order to have discrete or sparse adjacency matrices. And so, yeah, this is to say that if we need a continuous relaxation, then the computation, at least during training, cannot be sparse. So conversely, another approach, that is the one that we tackled with Andrea, relies on score function gradient estimators. This type of estimators rely on this smart trick where basically we are rewriting the loss on the left-hand side of this equation as the one on the right-hand side. And as you can see, while the expectation is still taken with respect to P of phi, we see that the gradient now is shifted towards the right-hand side, and so it's taken with respect to the log likelihood of our graph. So the log likelihood log P of phi. So this is this is really smart or convenient for us because it allows us to keep the computation sparse, as we will see, within the loss, or actually through our message passing operators, because A is just a sample. If you're already thinking about a Monte Carlo approximation, is a sample from P of phi, can remain discrete and sparse throughout to the computation of our prediction x of hat, and also the loss. Whereas all the gradient part is deferred to the computation of the log likelihood, or actually the differentiation of the log likelihood. So while the first evident disadvantage of this score function gradient estimator, at least is evident if you ever try to use any of them, is the fact that they often bring up a lot of variance in our gradients, so that this in the end can slow down the training curves quite a bit. However, for many applications, there are variance reduction techniques. This could be general purpose ones, or more specific to tailored to the use case that you have at hand, like in our case. But yeah, what I was already mentioning is that the most interesting part is the fact that the computation can remain sparse. So, and as you can see in both two scenarios, so with this pathwise approximation, or using the reparameterization trick, or the score function formulation, we have that we can take samples either from epsilon or directly from our adjacency matrix A, and then take the gradient after having sampled one or more samples. So this slide is to show that indeed there is some computational advantage. So with this, we are here comparing score function gradient estimator, or actually the training time or GPU memory during training for methods based on score function gradient estimator, and method based on the reparameterization trick. So because we are decoupling the loss from the likelihood, and the gradient is taken only with respect to the gradient, the message passing operation, which are the ones that would greatly benefit from sparse graphs, are those are actually those that allows us to maintain the memory footprint under control, as well as the training time. So you see that easily with the number of nodes growing, we reach easily out of memory issues here. Yeah, so again, this is to stress that there are some setbacks on using this, but there are also several solutions. Might be you may need to devise your own solution for specific cases, but there are solutions for these high variance setbacks. So lastly, on these topics, what I wanted to stress is that, okay, we have used probabilistic models. The main purpose so far was just to obtain some discrete or sparse graphs out of this learning process, but still we have a probabilistic model. So why don't we look at the edge probabilities that we learn and see if this actually can be insightful for us, for our application, and so to extract some relevant information out of them. Of course, this is not necessarily the case in all scenarios, because the training and the learning process need to be well posed. But anyways, if we are able to obtain such edge probabilities, indeed this provides valuable insights about for explainability purpose, and also in the end, on top of that, also achieve better informed decision making. One interesting issue in this setup is that okay, graphs in this case are latent variables. So, and as such, in real data, we don't have any observation about them. So this makes extremely hard for us to evaluate whether the edge probabilities that we are extracting from data throughout our end-to-end learning process are actually meaningful in any way. So this is an inherent problem. So we it's really hard to think of a dataset where we have such ground truth in order to assess whether the learned probabilities are actually calibrated to the true hidden ones. So what we can do is, of course, visualize and see if expert can confirm that this is meaningful or reasonable. But what we have decided to study more in detail is learning guarantees that allows us to some way bypass this problem. So we study from a theoretical perspective whether we are able to, in some ways, to learn the latent distribution and learning in a way that is calibrated to the to an unknown model that existed. So what we find out is that if we are able to minimize certain losses that allows us to say that are equal to 0 only if the two distributions that we see here are actually identical. If we are able to minimize them, what we are saying is that we are perfectly matching the distribution of the output from the data generating process. So it's matched by the distribution that is output from our predictive model. Okay, so if this happens, what we can say is that under certain assumption, this is not by default and is not in general true, but under some assumption, what we have is we know that also the probability distribution associated with the latent variable needs to be equal to the true one that generated the observed data. So while this is not true in general, for graphs that are stronger, actually not stronger, but milder, these conditions for which these results hold are much milder. So this is reassuring that indeed operating with graphs in this way could provide interesting and reliable edge probabilities. So yeah, so this concludes the part related to latent graph learning. And so if you have any question at this point, I'm happy to take them. Otherwise, I will move on to the last challenge. So yeah, there is one question. I have two questions, actually. Assume we have a prior graph created by an expert in a field. Would the latent graph create a better graph compared to such prior graph? This is the first question. The second question is, in case of prior knowledge is required, example, a physical system, can we enforce the prior graph knowledge into the learning pipeline? Okay, so yeah, these are two extremely relevant questions. So regarding the first one, if they relate or not to each other depends, first of all, on the approach that you followed while extracting this graph. So for example, if you are computing this graph as a Pearson correlation of the time series, what you have is the Pearson correlation between the time series. So a measure or estimate of the linear correlation of all pairs of time series. If you're following the last approach based on task-oriented optimization, so basically optimizing the downstream task, what we will obtain is simply the best graph, at least according to the optimization procedure that we devised, to optimize the downstream performance. So in this sense is what Andrea was calling a Lagrangian, in the sense that is really oriented to optimizing the final performance of the model. So depending on the graph that you are giving or you are considering as a prior, this may or may not match. So typically, you can reinterpret the relations that are extracted as would this relation help me make a better prediction to that time series or not? And then enforcing some sort of sparsity prior, where we try to maintain the degree of each node small. We are trying to promote those solutions that look only at the most relevant relations. Yeah, so this is for the first question. Regarding the second one, in case of prior knowledge is required, can we? Yeah, so there are different ways. So the short answers is yes, as far as you can design a probability distribution, for example, P of phi, that reflects that prior. This could be, for example, if you know that you have several physical sensors deployed in an environment, and you know that sensor too far apart in this physical environment have no relation at all, then you can enforce it in your probability distribution by simply setting to 0 those parameters. This, of course, extend a little bit beyond that. For example, if you know that the graph that you're looking for should be a sort of tree or a tree-like, then this is trickier to parameterize, but still, in principle, it is possible. So, for example, in our case of KNN graphs, our and also of others, it's not always easy to do that. Or actually, it is easy to design, it's not necessarily easy to optimize. For example, for score function gradient estimator, what you have as well to do is also to take the gradient of the log likelihood. Okay, so but the log likelihood of random extraction of k nodes without replacement is not so easy to write it down, and so to optimize analytically. So in our case, we rely on smart optimization from other people that find a numerical approximation of that and turn out to work well. But so depending on the prior that you want to enforce, this can lead to easy or hard solutions or parameterizations. Okay, so oh, thank you. So, okay, I think that if there are no other questions, I can move on to the last part, which is model quality assessment. This last part addresses the point that, okay, we have all these models, we have several okay, so we have all these models, we have our data, we have our prediction. Now the last question, of course, is always to, okay, but how good my model is. Indeed, our losses already provides us as a metric of goodness of fit, but it's interesting to see that as the number of time series grows, the length of this time series grows, then we may have also intricate interdependencies among these time series, can make a single number out of our training process a little bit restrictive to understand what is going on and if everything is working as expected. So beyond asking whether our model is good, we also want to ask whether our model is optimal, and where if there are regions or aspects, for example, the temporal processing or the spatial processing that would benefit from some further designing improvements. And lastly, of course, the question is, okay, now that I identified where the model may need improvements, now I need solutions or guidelines to act in order to improve, to make these improvements. Indeed, here I spoke about optimality. Optimality is, in general, depends on the criteria that you choose. It could be, for example, as I said, optimizing a predictive loss, like mean absolute error, but needs not to be like that. So we will see why and how relational information also within the task of assessing the quality of our models can be relevant, or actually the solution to make this process feasible. So a typical scenario that we are all facing is that we decided whether model FA is better than model FB based on the performance that we see on the test set. And then we say that model A is better than model FB if the performance that we see from one model is statistically better than the other model. And we say that a model A is in general, within a family at least of models, is the optimal one if there are no other model that is better than that. So this is pretty standard, and what we may encounter often is that, okay, say that I have this model FA, I may consider it good enough, or actually I may say it seems working appropriately, but I hope to make a better model. How can I say whether this model is the optimal one, or I can move forward or start working on it even further in order to improve it and find a better model? So this is a question that is hard to answer, because either we are still in the process of changing our models and finding a new one, until we find an actually better one. But if we don't find it, we still don't know whether we should look again for it or not. So unless we have, of course, some prior knowledge of for example, the level of noise that we have on our observed data, that of course this somehow sets the baseline that the baseline that we want to reach. So another interesting approach to model quality assessment, and this is why I introduced the previous slide, is that of studying correlation among the time series. Studying correlations is a way to understand whether in our predictions there is, or actually in the data that we are trying to model, there is information that we were not able to extract from data. In fact, here, consider this prediction residual, so the difference from our prediction X hat and the true or the actual observation from the monitored environment. This difference allows us to understand better whether there is optimality or not of our model. So in particular, if we see that there is some dependencies among the residuals, it means that there is a structural information left in the data, in our residuals, that our model was not able to extract. So in this sense, there is a margin for even further improving our model, because there are structural information in that data. So residual correlation analysis in that sense is independent from the type of performance metrics that we are interested in. Of course, does not tell us how much I can improve. Just say, look, there are some data that is correlated, so probably you should you could make it better, but doesn't tell you how much. But in the end, this is also interesting because it doesn't need to be a comparative analysis. I don't need two terms and say, okay, looking at those two, I can say the one which one is better. It's an absolute answer in some sense. So here we're talking about correlations. Most of the research so far has focused on serial correlation, so correlation along the temporal dimension, but there are also works that study correlation in the spatial dimension. Here I'm presenting an approach that is spatiotemporal, so address space and time at the same time. And so this works as follows. Basically, from our data, we have that at every time step, we have our graphs and our observations. So we can construct this spatiotemporal graph by connecting not only the edges along the spatial dimension, but also the temporal dimension. And by looking at single statistics of correlation, and these single statistics are the sign functions that you're seeing here. So the sign of the inner product of the residuals. This is probably the simplest way to check whether there is other direct or indirect correlation between the two residuals. So well, by making these averages of all this sign, we are designing pretty simple and straightforward test that allows us to understand whether there is some correlation left in the data. Well, these are split into two parts because one addresses spatial correlation, so the one in red, and the other addresses only temporal correlation. So here we have these W's, which are the weights, which are basically non-zero for all the edges of the graphs, and can set a sort of influence or sort of importance of different edges. So the most important part here is that while correlation in principle, so while studying correlation in principle, we should look at all possible correlations that are existing among the residuals, so gross, square, quadratically both in time and number of nodes. Here we are only focusing on the most relevant ones, which are the most all the possible connections that are more likely to lead to correlation. So this is why, again, graphs allows us to design statistical tests that are statistically powerful, although the data dimensionality grows a lot. So this, in the end, thanks to the fact that we have a sign, leads us to distribution-free statistical test, and also this scales linearly in the number of nodes. Okay, so this is a test that can be applied globally at the graph level, considering space and time altogether, can be split, looking only at spatial or temporal at once, but can also go into more finer detail by looking at single nodes, or for example, single time step, or even more localized both in space and time. So this concludes actually the parts where we are addressing the many challenges that have been not resolved, but where substantial research have been carried out. And now I would move on very quickly on future directions that we see as interesting and relevant for future research. So the first and foremost is probably this about hierarchical modeling, where as we have seen so far, the STGNNs, or the models that we have considered so far, look at the data as they are, so with the same fine-grained scale with which data comes, but also considering higher order dependencies by creating hierarchical structures like pooling of nodes or even along the temporal dimension. This allows us to consider both coarser grain scales, but also at the same time reach farther apart information within our data. And in the end, also, it's from an application standpoint, it's also important in certain scenario to produce forecastings that are at an aggregated level. I think, for example, at power load forecasting, we may not be interested at the single household predictions, but maybe a more aggregated level. And in the end also allows us, as mentioned here, to reconcile all these different predictions made at different level in order to make a more reliable predictor. Another interesting approach is that of considering state space models. These state space models has the intrinsic advantage of being in some sense Markovian, in the sense that observations or predictions are made only from the current state of our system, and this system is updated from the previous state at every time step, and could be possibly also driven from an input graph. So this is decoupling all the three dimensions, input states and outputs, allows us to have different type of graphs with different relations that can allow us to either in the former setup of a hierarchical modeling, or for other reasons to have different graphs for different purposes. And this is also amenable for the reason that this allows us to make prediction only when needed. If we needed to prolong the state update, we can do it. If we observe, for example, a certain point observation from the model system, so true observation of y of t, we can also feed back in the same ways as Kalman filter operates for linear system. We can feed back this information back to our system and update and improve our state estimates and repropagate forward with an improved modelization of the system. Another relevant scenario is that of inductive learning, where several issues can occur to our monitored environment. For example, we can see changes in topologies. We can see new node be added to our network, for which, for example, we don't have node embeddings yet. So we need to make some adaptation in order to apply our model to these new settings, or even transfer the entire model to a new network. This is useful not only for forecasting, but all sorts of applications related to this type of data. And of course, as we change the data that we are dealing with, this can also incur in performance degradation. That is what we are trying to maintain as expected. So lastly, benchmarking is another topic that needs to be addressed in the future, at least according to us. We have some large data sets, open data sets. This spans energy analytics and traffic flows mainly, where this type of data, this type of models have been designed for since the beginning. But this is, of course, doesn't provide yet a comprehensive benchmarking environment, at least in my opinion. We also have some software like the Torch Spatiotemporal that Andrea and Ivan have designed, but also basic TS are useful resources in order to try to standardize model implementation, evaluation, cross-validation, and so on and so forth. But yeah, we are not as close as to what, for example, Open Graph Benchmark is now. So all in all, to conclude, what we have seen is a framework for modeling time series, and this combines the deep learning for time series and deep learning for graphs. This combination of the two is turned out to be extremely fruitful in several applications. Doesn't need to be always like so, but we have seen that this inclusion of relational biases in one model was really a game changer in several tasks. And this not only allows us to improve performance, but also more at a fine level, we have the possibility to share parameters. So we have a better ratio between training data and model complexity, and also overcoming all those issues that may be present in this data, for example, missing data or other irregularities in our data. Finally, we feel to suggest global local models as a safe starting point for modeling this application producing data similar to the ones that we have described to you so far. So, of course, we have discussed the challenges. I also want lastly to point out to our tutorial paper, which is the one written here at the bottom, and also the library, Torch Spatiotemporal. Both of them, I hope you find it useful. We are pretty proud of both of them, and if you have any feedback on them, also please write us to us. So I hope in the end to have brought you some interest in these topics, in all these models, and also these solutions. I think there is huge room for exchange of ideas with related fields. And so please reach out to us anytime if you have ideas that you want to talk to us about. And here I leave you with the link of our group, Graph Machine Learning Group in Lugano, Switzerland, where you can find also a list of publication, all the materials of this tutorial, and of course also our contact information. So at last, don't forget to fill in the feedback form for the tutorial that you might find on Slack, right? And probably also we can post it here in the chat.
Here it is.
So thank you, everyone. If you have still any question, please ask. I'm free to address them the best I can. Also, Andrea is here, so. Okay, yes. So the feedback form is in the chat right now.
There's a question that came up in the Q&A if you want to take a look.
And the Q&A on Slack, you mean?
On the Zoom Q&A. I can read it out loud and paste it in the chat.
Oh, okay.
The question is, in scenarios where multiple time series have irregular time intervals, some occurring more frequently than others, what are the recommended approaches for data representation and graph neural network architectures to effectively learn interdependencies among these time series?
Okay.
I think you want to answer it?
Okay, so it very much depends. Maybe you have other takes on this. It very much depends on the level of the scale, if you will, of these that you require your predictions to be. For example, if you really need fine-grained predictions, then it's probably easier to create some sort of upscaling of the less frequent time series. But this need not to be the case, because we have seen, for example, when you're trying to combining say covariates or exogenous variables like those coming from the weather, or you want to encode in a traffic prediction model, maybe the hour, so to identify peak hours, but maybe minutes are not so relevant. So in the end, what you just bring in is just an upscaling of that information and use it to make your predictions. In that sense, is not necessarily big of a problem. Of course, if this each time series is less regular, so produces observation asynchronously or very regular time steps, then there are models that probably are more appropriate to them to address them. Could be, for example, continuous time models, where they try to address these irregularities. So they take in data as they come, and then they propagate along the temporal dimension, and but they don't need to have such a regular information coming all the time. This is, I'm assuming, the time series are not on the same sampling rate, right?
Yeah, I pretty much agree. So like if you have some pre-processing that you can do to deal with this irregularity, and this pre-processing can also be something as complex as like fitting some imputation model or some rescaling or as simple as an upsampling, if it's just a matter of having like a different frequencies of the observation, then it's fine. If it's something more structural, that the observations are by nature like intermittent or something like that, then continuous time models are the way to go.
Yeah. But for example, so in traffic forecasting, the data that we have is actually the passage of a car under a certain sensor. I don't know how to call it. And like, so you have, in principle, a synchronous observation, but in the end, the data that we have available in the end collapse all the information within mostly, I would say, 5 minutes.
5 minutes windows,
yeah, 5 minutes windows, and then they count how many cars have passed through that lane within 5 minutes. So in the end, this is another way to actually downsample the data that you have. Depends a lot on the application, I would say.
Yeah.
But on the other spectrum, if we are trying to deal with a scenario more similar to temporal graphs, then probably those techniques are not the most appropriate.
And then continuous time models, I think, have an edge.
Awesome. There's also one more question, but I'm not sure if it has already been answered. I put it in the chat again. They say, when can it be beneficial to learn an adjacency matrix that depends on time as well? For example, we drop or create new edges between time steps. Are there works that do that?
Yeah, I think like the NRI paper, so the neural relational inference paper that was cited in the slides, and was the graph learning approach based on the reparametrization trick. In that one, the graph that you are learning is conditioned on each window of observation, so it is dynamic. It's like the actual output of the model is conditioned on the observations at specific time steps. Regarding when these can be beneficial, again, it's really like problem dependent. Like if you have like a physical system where like the position of sensors, for instance, changes over time, then having something like that would be really, I mean, the only thing that would make sense to consider to learn this kind of dependencies. If instead what you are modeling is something more static, then it might be okay to just learn something which is static. Another, I think, important dimension of this is how fast these changes in the topologies are happening. Because if changes are happening slowly over time, then what you could do is something similar to continual learning, where the graph that you learn is static, but you also have some mechanism to have it like adaptive, so that after a while you can check whether that kind of topology is still valid, is still giving you adequate performance, and if not, you can update it. And yeah.
Awesome. Any final questions from the audience? All right, if not, thank you all for this fantastic tutorial. We really appreciate the time and care you've clearly put into this, put into making this tutorial so accessible and informative. Please feel free, everyone, to continue discussions in the tutorial discussions channel or by directly contacting the organizers. As a reminder, the tutorial feedback form is linked in the chat. We really appreciate any feedback that you may have. And we will also share this feedback with the organizers themselves. So that brings us to the end of this first part of today's LoG conference. Please join us later for a keynote from Xavier Bresson and oral presentation. Thank you very much. Have a great rest of your day.
Thank you.
Thank you. Thank you all.
Bye.